So today, here we are in part 2 of our series on statistics. And as I said, we've entered in our data. We confirmed that data entry to make sure there's no major outliers, no typos, things that we typed in wrong or otherwise were unusual that really shouldn't be part of the analysis. So now, before we run the analysis itself, we've got some things to consider. And so we'll just start today with a really basic overview of the analysis and segue into the goal of data review, which is to prepare our data for the analysis, which that'll be our week number 3 of our session next week. So the standard analysis really across the industry, what typically is used to actually process our data and make some conclusions is the analysis of variance, or AOV. And so statistical variance really is a measure of how spread out the data is about its mean. So the goal of AOV is to dissect that variability in the recorded assessments to understand whether the differences we have observed between the treatments is due to the treatments themselves or just by random chance. So there is controlled variability that the researcher had a hand in from the treatment and the blocking structure that was put in place as part of the study design. Then everything that we cannot control, that is called the experimental error. And so the overall approach of the analysis is to consider that the observed response has really 3 components. There's the baseline response if nothing had occurred in the trial, really that baseline or overall mean. Then you have the effect that the treatments and the blocking specifically had. So those were coming from our controlled effects. And then the effect that just the random influences had as well. And so since our goal is to draw conclusions about the treatment effects, we really would want to estimate what that random and uncontrolled effects are, because then that really lets us zoom into the controlled effects, the treatments. If we kind of know everything else in the equation, then that lets us focus in then on those treatments. If we're going to do that and kind of understand those uncontrolled effects, we're gonna maybe need to make some assumptions about their behavior. So that's really where these assumptions of AOV come from. We've got these baseline things that we can assume. If we can believe that these things are true about our data, then the results that we get when we run the information through ANOVA, we're going to feel good about. So the first one is homogeneity of variance. Really, that's if the variances of the different treatments are approximately equal, at least comparable to each other. So if a treatment is much more variable or even much less variable than the others, then the ANOVA will not work. That consistency is needed for us to trust that no matter what treatment we're looking at, it's about the same amount of variance as we look to try to split it all up. So there's some tools, of course, to try to determine and make sure that we can believe that there's homogeneity of variance within ARM. We can look at a box Whisker graph, which we talked about a little bit last week. Looking at the heights of those boxes give us that rough visualization of the amount of variance in each treatment. And then if you want to be a little more rigorous, there are statistical tests. So we can have a nice black and white, mostly black and white answer, if you will, to see if we can say we're 95% confident that there is no homogeneity of variance, for example. And so the statistical test for that would be the Levene's or Bartlett's. Both kind of do the same thing. Levine's is usually the one chosen for its robustness, but either one are tests for the homogeneity of variance. The next assumption is that the distribution of errors is normal or bell-shaped. If we have this, if we can feel pretty good that we've got that normal distribution and equal variances, then the math can kind of do its thing because we can calculate a reasonable guess for the amount of error based on that standard bell-shaped curve. And so that's really why typically these are kind of the biggest two because it really makes the math work, if you will. So there's actually a few different tests. For the bell-shaped, the Shapiro-Wilks is kind of the overall general test for the normal distribution. And then there's also skewness and kurtosis to kind of look at the way that the bell is, if it's too tall, narrow, too wide, or skewed, things like that. Another assumption of AOV is additivity of effects. And so specifically of treatment and block effects in an RCB design. So for example, the effects of a treatment like an insecticide or fungal attack are likely to be multiplicative on the count of the population because it affects a proportion of the insect population. And so it really kind of multiplies down if we're starting to limit and attack the population itself, then you're obviously hurting the population and the potential for growth. So it really kind of is multiplicative, which is not what we're hoping for in the sense of these assumptions. So really then perhaps a more suitable assessment to analyze instead of just those raw counts would maybe be like a percent of untreated calculation. Still, we're still assessing the thing we care about, but the data itself fits that distribution and the general idea of this additivity of effects. This one is a lot harder. There is no just kind of here, run this test, or here, look at this tool, and it'll, you can kind of get a sense of what it is. It's a little more philosophical, if you will. So a little bit trickier, not really a lot of tools in ARM for that, so we won't spend too much more time on that. But yeah, kind of falls back onto the protocol setup, your study design, kind of what are the assessments we're taking, and what type of study are we running, and those types of things probably are kind of just built into the way things are done within the industry. Last assumption is independence of errors. Really that one assessment does not directly impact the next one or the previous one. So this is also a little hard to test for. Generally not too big of an issue when we're looking at the data. Really, you're just trying to make sure to not introduce bias in the assessment. So a little bit more on that ahead of time. Not much we can do kind of after the fact, diagnose, but hopefully things were taken into account for when that assessment was taken. Probably the assessment heat map that we looked at last week, that would be maybe useful to detect some of those types of things. The bias in the assessment, if there's an edge effect that suddenly then plot, assessments kind of towards the edges are inherently different than the ones in the middle. That's a sort of bias where there's not really the independence on each plot is totally separate from one another. Or if you're taking a subjective rating and as you go through the field, you're starting to be kind of swayed by how all of the other ratings are going or things like that. Those types of things. Again, kind of more of the baseline, how research is done, make sure to be careful with bias and stuff like that. So not a ton of tools for us kind of after the fact. And there was a question, so to reiterate, really both of these last two, both the additivity of effects and the independence of errors, we really don't have a test. We can't quite just run a statistical test and find out. It really kind of is more on the shoulders of the setting up for the assessment itself is really where that lies in. So yeah, those are a little trickier, and so that's why kind of really most of the discussion it kind of filters down to the top two, because really those are what we can look at and diagnose, and these other two are more of those behind the scenes planning things, stuff like that. So of course, then the big question for us is, well, what if we don't quite check off all those boxes? What if those assumptions are not met? And so really, the super short answer is we can't trust the results. If our assumptions are not met, we can't trust the results that we would see on the report, even though if we tell software to run a report, it's going to give it to us and it'll give us all sorts of numbers and letters and all of that. But if we're not careful, we can't just blindly follow that as what is really true unless we take a look. But luckily, we do have some options of things we can do before just throwing out everything and saying, oh, well, we didn't match the AOV, so we're done for. There are some things in our toolbox that we can do. So the first one is data correction transformations. Really applying a transformation to all of the data points, very equally in a assessment. And the goal is to correct the underlying distribution of the data, and thus the distribution of the errors, which was really the focus on the previous screen here, without affecting the results. So we're performing that same calculation on every single data point. So we are still treating things fairly, and thus, mathematically, we're still making the analysis on the same results, if you will, even if the distribution of those numbers now is changed, because that's really the goal. So there's three main ones used in the industry, and thus that ARM uses. The log transform, that's great for taking counts of things that occur in clusters, like insects. That typically is a log normal distribution, and running it through a log transform will bring it down into more of a normal distribution for us. The square root, that is good for counts of things that occur at random or really rare instances. You'll have an assessment where there's a whole lot of zeros and then a 5 and a bunch more zeros than a 2. And very rare. Most everything is just there wasn't anything here, but every so often there's something that pops up. And so that's a Poisson distribution, and the square root will kind of smooth that out for us. And then the last one is arcsine, the full phrase arcsine square root percent. It's a big long equation on that one. And those are great for percentages. That can end up kind of being a binomial distribution where you kind of end up with two peaks maybe instead of just the one. And that arcsine will kind of bring it all together back to that normal curve. So that ends up being kind of a lot of what we'll see in ARM today. Is trying to utilize some of those data correction transformations. But there are a couple other options. There are spatial models, which try to recover information about hidden variables across the field that we maybe didn't account for. So in ARM, we've got 3 trend models and 4 nearest neighbor models. Typically, these are used really only when the blocking design fails. So in the perfect world, as you're setting up the RCB design, you kind of know a gradient that may be out there. We block for that to try to make a block as homogeneous as possible. If that fails, if there was something else out there that we we didn't know about, or what we thought was there wasn't. A spatial model really says, well, blocking didn't work. Throw that out. Let's just try to figure out for ourselves what was going on out there. So usually not super high in our to-do list for things to utilize, but it is a really nice backup plan, if you will, if we're really really struggling with some of the other things we can do. Then finally, there are some non-parametric statistics. So that really just throws out AOV and don't even have to worry about its assumptions. Let's run a totally different analysis, really all based on ranks instead of the means. So we rank the assessment values, and that's really kind of our main point that we're utilizing in the analysis. And then we can still run a mean comparison on the mean of those ranks. So it ends up that our kind of final report looks very much similar, and the non-parametric tests can still be done pretty much in the exact same report. You don't have to go somewhere else in ARM or outside of ARM. It'll kind of tuck nice and neat just right next to all of the other assessments that we're doing. In general, the non-parametric tests just have less statistical power. So that's why we usually don't start there. AOV has a lot more power, if you will, statistically speaking, of finding the true differences. So that's usually where we try to start. But when all else fails, we've got those non-parametric tests that can be done instead. All right. So that's enough philosophy, I think, here. Let's dive into ARM, which I thought I had open, but did not. So let's log in real quick, and we're going to, got a trial that, kind of rigged up, of course, kind of like what we did last time, where it's like, well, trying to rig the system a little bit to have good examples for us. So probably in practice, if you were to open up your own study, hopefully you won't have quite as much quote unquote excitement going on necessarily. So really the main tool we're going to utilize here for our data review is the Column Diagnostics panel. So that would be right here on the assessment editor. And to save a little space, I think I'm going to unpin my navigation bar. So we have a little more room on the screen. So all the way over to the right, we have our properties panel. At least for me, I have that displayed by default to start with. But I am going to unpin that, so that is hidden. And then we've got the Column Diagnostics way over here on the right. And so he's needs a little bit more width. So I'm going to drag him out for us. So whichever column that I am clicked into with my cursor, that'll be what the Column Diagnostics is going to give us information about. And last week we were here for a little bit with the data confirmation. So we did talk a little bit about this diagnostics table at the top. The very top information here at the start of the table is really just stats, if you will, of the box score, if you're a sports person, of kind of what is going on in this assessment. How many data points, how many unique numbers across those data points, how many are analyzed versus maybe are missing or thrown out because they're damaged or something like that. Really, our focus here today is these four here, kind of in the middle of the table. This down just a little more. And the names hopefully look a little familiar because they were just on our slide a moment ago. They are those statistical tests that we can run to test for those assumptions of AOV. So we've got the Levines, which is running for the homogeneity of variance. And then for the normality, we've got that Shapiro-Wilks, skewness, and kurtosis. So in this table, we have two columns at the moment. Raw is referring to running the test on just the raw data values, just the values themselves, run the test, see what the results are. What we care a little more about would be the second column, which is labeled IID. And in this spot here, it's really referring to the residuals. So statistically speaking, we can test just the, we can test just the raw numbers, or we can test the errors. We were talking about that, you know, the experimental error that we really care about in the philosophy that we mentioned. And that's really what we would do here with the residuals. And I don't know the math of kind of how you go in and calculate those residuals, but then those values there in the assessment, that's what we're testing for. And that's really kind of the more modern statistical approach, is to be looking at those residuals and deciding if those fit the assumptions of AOV. That's really what we care about, is the error term, you know, the errors, trying to figure out what's within there. And so that's where we kind of spend our focus here. And in this table, these numbers here are p-values, really the end result of a statistical test. So the p-value is a probability, and really in these cases, we are hoping for no significance. In other words, if we had a very small number, you know, less than that 0.05, that typical 5% alpha level, if we were lower than that and the test is significant, that tells us something is wrong. That tells us that the test for homogeneity of variance failed, or that normality failed, and there is something that is not fitting those assumptions. So in our first example, we had success. We don't have anything that is less than that 5% cutoff. So we have a fair amount of confidence that there really are no departures from our AOV assumptions. And as such, we really don't have to take any corrective action at all. So what we recommend is just clicking the checkbox next to IID. And this is kind of the reason we used IID as the heading here. Really just because it's going to add an action code to this particular column. And the IID, really all it does, it actually is not an action in this case. It's really just marking to say, hey, I've looked at this column. We ran the tests for the AOV assumptions, and nothing came back to be concerned about. So we don't have to take any action. And that's really what this is saying. You know, if we left it blank and just moved on, sure, we hopefully we remember that we've already looked at this trial, but it's a nice way to kind of stamp, yep, this has been reviewed, we've looked at it. Then we can move on to the next column. There's a button right here that literally just moves us over to the next assessment, or I can click on, you'll see kind of how this table changes. If I click from one column to the other, again, whatever one I'm clicked into, that's the one that these tables will refresh and calculate based on. So now we're into column 2. We come back to this table. We have a little more going on. So in our IID column that we care about here, there's actually something highlighted for 0.02. So ARM is kind of helping us to see that we have significance here in the Levine's test. We're really not too worried. These are highlighted here in the raw column that both the Shapiro-Wilks and skewness did as well. But because that's the raw column, we're really going to focus on the IID column here. Those are the results we care about the most. Real quick, on that last column, we had the IID. If we left that with raw selected, you're right, nothing would change. So both IID or being totally blank has the exact same end result, which is nothing additional will happen in the analysis. Just putting on that IID is just a nice way to stamp and say this has been looked at by somebody that has reviewed that there is nothing to do, as opposed to a blank. Again, you don't quite know for sure. Did somebody look at this or did it get skipped over on accident? Good clarification there. So now here in column 2, we aren't quite as lucky to say we don't have to do anything. Our Levine's is failing. So what we can do, of course, is now consider some of those data correction transformations. And ARM has actually done that here and ran a couple of those tests. So I can see that with the AL, which is the automatic log transformation, that would fix the Levine's. But it looks like it then does introduce some trouble with the normality. Whereas with the square roots, that looks pretty good. That looks like that might fix a lot. So we can kind of manually look at this table to figure out some options. But a little bit quicker route would actually be down below with this recommendations table. And so basically here we have a nice quick summary of those Levine, Shapiro, skewness, and kurtosis. This is the test statistic value. So if you're statistically inclined and curious about just the test statistic for Levine's, that's this value here. I would contend as a non-statistician, I like these values more because they're the p-values. They're a lot simpler to just plus or minus that 5%. How do I feel? This obviously is a little more involved. I don't know what a 3.5 means as far as the Levine's goes, but some people may. So that's there for our option here. And then there is a recommendation. So ARM has looked at all the options and can say, well, if we use the automatic log transformation, that stabilizes the variance. Whereas Shapiro-Wilks, skewness, and kurtosis get the IID, which again is the recommendation of nothing. We don't have to do anything. We're all set already. And so we ordered these really in terms of overall how much we should be concerned about. So Levine's and that homogeneity of variance is really the biggest concern, just as far as that trusting the analysis in the end. If we don't have equal variances or close enough to equal variances, we're really in trouble. There's not much we can rely on in the analysis as we're splitting up and looking at the variances, because it's be kind of a bit of a crapshoot at that point. So Levine's is target number 1. Sometimes you can get away with a little non-normality, especially if you have a lot of data points. Then things end up being smoothed out enough that it's not such a big deal, but Shapiro-Wilks should probably still be taken pretty seriously. And then skewness and kurtosis, again, if you've got enough replications, enough plots out there, then if there are just some slight departures, maybe you can get away with it. If it's kind of one of those really close calls, probably best to bring in a statistician who can kind of take into account your type of experiments and things like that. So a couple of questions here. The p-values, so both up here and kind of the decisions being used down on this table. The question is, are we using that alpha level? I kept referring it just as the 5%. Are we really using the alpha level that we have in our print reports on that AOV section here, when we're doing the analysis, we can choose our own alpha level. And depending on the test, a little bit bigger selection there, or is it just 5%? And in this case, on the diagnostics panel, it is just 5%. So the mean, and we'll talk about this option a little more next week, but the significance level that you're running kind of overall for your mean comparison test, that can be swayed. That can be a decision you make based on your type of study, the objectives of the study, what's your penalty of failure. But the test here is really just a little less leeway, I guess you could say, where we're focusing we're going to use the 5% as kind of the standard metric, if you will, for making decisions. So that's a good question. Everything here we're highlighting is based on 5%, and all of the decisions and recommendations here are always going to use 5%, whether or not your alpha level when you run the analysis may differ. It'll always be 5%. And then the next question is the perfect segue here, because what we have right now with these recommendations is just looking at the data, just the numbers, which things work, which things don't. We can, however, consider and take into account the type of assessment that was performed. So using this basis option right here, kind of this first option in the recommendations section, right now we have it set to assessment values. So ARM knows only the numbers in that column, and it can figure out and consider all the different types of data corrections based on that. But we can point ARM to the action codes field or the rating type or the rating unit. So that way it knows what type of data this is. In my case, it's a count. So if I select rating type, you'll see it recalculates, and we actually have a different recommendation here. Because for count data, square root is probably a better fit. As we mentioned with those, those underlying distributions, is kind of the reason that there's the standard that people use across the industry for certain types of data and what fits. So basically, ARM has changed the number of possible transformations that it can do to say, oh, well, if we're doing count data, I should check out the square root first. Turns out that's a really great recommendation because now all four things are fixed. So this basis is really how you can instruct ARM to know a little more about the data that you're reviewing. And real quick, kind of the engine behind that, how it can know that is in the rating type or the rating unit field. You may have noticed that there is an additional column to the right called family. And that's really how this engine knows what this is. Because of course, there's so many different types of counts and things like that. That's really how it knows, oh, this is count data. So these particular transformations are the best ones to use for count data. As opposed to, if we scroll down quick, I'm sure we can find some other ones. There's a proportion. So that's going to be different. That's probably going to be more interested in the square root, perhaps, things like that. And some of them, of course, won't really know. So just some things that don't have a family, then ARM doesn't really have a lead per se on what types of things to do. But here's a great case where that really can make a difference as to the best recommendation to make. So in this case, we really have identified that the square root is perfect here. It stabilizes our variance and it matches with our count data. So I can either choose AS up top here, or if I double click in this table on that row, what it does is puts in that transformation code into the ARM action codes. You'll notice the data itself hasn't changed at all. So the nice thing is we're not adjusting any raw data. Nothing is being changed in the documentation of the trial. But when we go to run the report, then this is going to be instructions to ARM. Before you do analysis, you need to transform these data points to square root and then run the AOV analysis on those values. So that's all done kind of behind the scenes. And all we got to do is put in that action code in order to have that action take place in the analysis in the end. So we have tackled that one. So now I can click in here to anywhere really in column 3 to move to the next column. Now that we've kind of talked through all the pieces, really the quickest thing, at least for me, if I were going through the assessments of a trial, I usually don't even look at this table. If I want to go quick, my eyes dart right to the recommendations table and specifically this column. And if I see 4 IIDs, I know I'm good. And I'll just click on any one of them to throw that IID in there. Oops, I collapsed the wrong group. Let me just shrink some of these groups so we can see the information we want here. Okay, back on column 3. 4 IIDs mean everything's good. I don't have to do nothing. So just double click to add that. And then let's go to the next column. Okay, well, we don't have all IIDs, so then let's slow down and do a little investigation. Probably should consider the basis, and we are still pointed to the rating type, and this is a count, so we feel good that that's the right thing. ARM then knows what type of data we've got, and we see kind of like in column 2, just Levine's is problematic. And everything else is going to be good if we do the square root. So we can go ahead and do that. So hopefully, yeah, I feel like sometimes after doing the training on this, it makes it seem like this is kind of a long, painful process. But I think in actuality, you'll find, obviously, depending on the type of research, if inherently all your assessments are going to be in those different distributions, you maybe don't get quite as lucky as I am right now, where I'm getting all these IIDs. But it can actually go pretty quick. Again, even if I were to accidentally skip this one, it wouldn't be the worst if I didn't do the IID, but it is nice. So that way I know for sure somebody has looked at this column and I just don't need to do anything. So here's an example, no rating type family for, to be honest, I don't even know what this code is, disease loci growth. So we don't really have a good sense of what that might mean. In this case, I can change it though, because the rating unit is a percent. Oh, well, ARM knows what percent would be involved. Of course, in this case, it was irrelevant because we didn't have any departures from AOV, but just to show that basis does update it. So you're kind of notified if there's nothing ARM is going off of to see that. Really good question here. If we're making the transformation, then the p-values in the column diagnostics might not be the same as when we do a print report. So I'm guessing, I'm not sure, I guess with the transformation itself, I'm not sure that would make a difference. I'm guessing more commonly, the difference actually is related to these 2 columns. So the tests against the raw data points, 10 years ago, that was the de facto way to do the assumptions of AOV test. And that was really the one and only calculations that ARM did. And then once we brought in the Column Diagnostics, that was really the time we introduced the concept of actually we should be testing against the residuals. The industry has really moved to that direction. So there are still some spots where there's that old philosophy, that the previous set of rules and calculations that are, I guess you could say, still lurking in ARM. And certainly, of course, statistically speaking, if you preferred to do it that way, you sure can. But you can control that so that way on your report, you see the same p-values as the decision you made in Column Diagnostics. You can go under the AOV options. There's the descriptive statistics. And we've got all of those normality tests, the ones we've all been looking at, you can have on the report. And the option, this very first option here, would probably explain the difference. So you can control whether we calculate based on the residuals, which would be the IID column. So if you're using Column Diagnostics, you would want this to be residuals. The assessments matches up with the raw data column. And that's kind of that older approach that was done previously, where you're looking at only the raw data. So if you've made all your decisions based on the Column Diagnostics, then you run a report, and wait a minute, it's telling me my Levine's is significant. I thought I fixed that. That could be the deal, that you want to make sure that ARM is calculating based on the residuals within your report, so that way it matches what you were seeing and what you were basing your decision on in the diagnostics panel. So hopefully that helped. There is kind of in this same idea, real quick, the old method of checking against those raw values, that had a question that would pop up when you generate the report. So some people like that just for the simplicity, but then really it's maybe a little too easy just to wholesale take a bunch of actions. And really maybe you should spend just a little more time to look column by column to make a good informed decision. But that on the general summary tab of the options towards the bottom, there's this really long option to apply automatic transformations or treatment exclusions to data columns that violate assumptions of AOV. That's really that old system. So this, the calculations here, the questions and proposals for what actions to take are not going to match the diagnostics panel, because they are using the raw data column. They're looking at just the raw data, run the test, run Levine's. If it's significant on the raw data, then maybe we need to throw out treatment tube. So I recommend turning this to no, and kind of turning off that option, and instead using the diagnostics panel. It's kind of the more modern statistical approach. So great question. And if you did have any other troubles with a report not quite matching what you thought, feel free to send us an email with your trial and your report set, so that way we can kind of replicate and see what you're seeing and try to help track down what might be going on there. The other question is to understand all of these action codes. What do they mean? If you have a column that has codes in it, or if you just want to know what some of those do, just go ahead and click in the action codes field, really any assessment column, and either press F9 or this button here on the screen. And this will give you the full list of the different action codes that can be selected. And then there's a description of what that is. And there's also a report option to view like equations, the decodes and things like that, if you want to see that in your report as well. Okay, let me clear. Somehow got a drawing there. All right, moving along here, this column had IID, so let's move on to column 10. Same thing, easy peasy. One more thing I guess maybe if we wanted to dive in a little deeper on some of these, obviously in this column, we feel good, we could move on, but there are some diagnostic graphs that we can view. And in this case, I'm kind of stopping here because we've got the IID selected. And so there is, I might go 2 by 2, so it's a little easier to view. This is going to generate some diagnostic graphs for this data column here. And it's based on whatever code I have selected. Right now I've got IID, clicked on in this row, so it's going to give me IID graphs. And we'll do this again when we actually have a data transformation visible to us. So I can make this taller. I guess it won't let me. So this generates a PDF, and I've got 2 pages here. I'm going to zoom in a little bit so we can take a look at what it's giving us. For the IID recommendation, it prints on the left-hand side the graphs for the raw data, and then on the right is the residuals. So we have a box whisker of the raw data, so it should look pretty similar to what we did if we generated a box whisker like we did in the first session. This is for the raw data points, and then these are the residuals. So we get to see the Levene's value there to say, yeah, those box heights are pretty close to the same, reasonable enough for us to think that there really is no departure from the homogeneity of variance assumption. So we have a nice visualization of some of these tests if we don't want to just assume based on that p-value that we should go with it or not. Or if that's close, we have that question about, are we using 5% or our alpha level? Maybe if it's 0.07 and we're like, well, it says we can ignore it, but should we be concerned? This is a great way to dive in a little closer. So this next one is about the normality. So it's the QQ plot. Again, on the raw data, where it's very significant. There's no way it's a normal distribution, but with the residuals, you're actually looking pretty good there. Then on the next page, we have a histogram. Oops, I skipped one, didn't I? Spread location. So that gives us a sense of the skewness, not being too clustered, whereas these really everything's very much clustered. So in the raw data, there is really no hope for the normality, but the residuals actually are pretty well distributed. And you can see why here, the histogram of assessment. So you can see it's very much on the low end, and then there's a few high values. But if we're looking at the residuals, yeah, it actually looks mostly bell-shaped. So things ended up pretty good, and that's why in the end here on our results, all of the recommendations were IID. Even though obviously if we were looking at raw data, there would be a lot of things we were supposed to deal with. So that's the graphs here. Let me skip ahead. I know I've got one of these. All right, this one's a little messy. I'm actually hoping for, well, we can do this one. Because what I wanted to show then is maybe a column that has some transformation recommendations. Obviously, the end result, we weren't actually recommended to use AA. I'm just going to click on it for the moment to show that we can generate graphs. I'm going to do the 2 by 2 again here, just to compare and contrast. When we had IID selected, we were just comparing raw to the residuals. If we have a proposed data correction transformation, and we want to view the graphs, then we get the residuals on the left, which is again what we're kind of basing our initial decision on. And then we have the transformation, the residuals based on the transformed data. So in this case, we can kind of say, identify what might be wrong that we need to correct, and then decide, does this actually correct the issue at hand? In this case, Levine's was fine on the left, so we're not too worried. It ends up being fine on the right. Shapiro-Wilks is significant for the QQ plot. So we're not super confident that there's a normality assumption we can make. And actually, the AA does not fix it. So kind of starting to get an idea why AA wasn't the final recommendation. And we can do the same thing for these other graphs to see that, yeah, we don't really quite get what we're hoping for in the end with that AA recommendation. So that's a way to really dive in deeper, and that is just generating a PDF report. So you could save that and use it in anything you might want as well. So thinking of this column, we clearly learned AA is not going to get the job done. And in our summary, we can see, yeah, we didn't have much of a hope for that recommendation actually resolving the issues. It looks like it would have fixed the Levine's was just fine in the residuals anyway. So that brings us to another category of actions we can take. So here, that Shapiro-Wilks never could get fixed with those data transformations. All of those do not actually improve the normality to an extent where we can feel good about our analysis. So we dig into our toolbox and say, well, in that case, if we really are out of options for just correcting the data, let's go and use non-parametric statistics instead. So that is the AR recommendation. Really, in a sense, you're applying an automatic rank transformation in some regards. So I'm going to double click that, and that'll adjust the code there. And again, the nice thing is we're not changing the data. We're just going to pass instructions to ARM for when we run the analysis. And in this case, we're not even going to be looking at the treatment means. We're going to rank the data. Then we're going to get rank means that we can run our mean comparison test on. So it'll actually fit just in the regular AOV report. This column will be there just like all the others. There'll just be some footnotes to say, hey, we actually didn't run AOV here. We did the non-parametric statistics. And depending on your study design, real quick, I know it's here. Depending on your study design, it either does the Kruskal-Wallis, the Friedman's, or the aligned rank Kruskal-Wallis analysis. That kind of whatever ranking method you might use, ARM will decide that for you based upon your study design. I think it's Friedman's for RCB, but we could dig in the help to find out for sure. All right, we could keep going and real quickly be selecting our codes to get to the end. And yeah, there are some ARs. And we made it to the end, and that's an IID. And you'll notice this column had an existing action code, TY2, that would be a yield transformation. So you'll see when I double click, it has just added on the IID action code. So it is possible to have more than one code in a column. And ARM will just read to know that there's more than one thing going on here. Okay, so we have covered, I think, pretty well the diagnostics panel. Just a couple more tidbits here. At the top of the panel, there is an option to include spatial models. So this is usually off by default, because as we said, it's kind of a last-ditch approach. if we have a good idea that our blocking did not succeed, then we would turn to this option. I don't think I would just blindly turn it on just because I'm curious, or at least wouldn't utilize these recommendations necessarily unless we had a good reason to. Maybe that first time digging into spatial models, again, it might not hurt to consult a statistician if you have one available, just to understand what should I look for to know whether this makes sense or not. And I won't spend a lot of time on the calculations. A lot of it goes over my head, I'll admit openly, but what it does do when we turn this on is put a whole nother set of recommendations in the toolbox for the diagnostics panel. And that's those different spatial models, the trend analysis, the nearest neighbor analysis. Those all become part of the menu, if you will, that ARM can choose from. And in this, in this assessment, we didn't have any departures from ANOVA, but there are two more test statistics, the AIC and the BIC, that again is kind of in that spatial realm of figuring out, is it appropriate to even run a spatial model or not? So we'll leave that kind of out there. And one last note, all of these calculations that we're doing, all are actually being done in R, kind of behind the scenes. So there's a button here. You can actually export all of the code that ARM is using to generate this information and send it out to RStudio, or just the R script itself, or SAS as well. So if you wanted to see behind the scenes of what we're doing, or if you wanted to take it and tweak it from there or whatever, that's a simple export of really the commands, the commands used to generate this analysis that we see just on this panel. All right, well, we blew past our time. I appreciate the questions throughout the session. That was really great. If you have any others, and the one at the tail end, hopefully if we have time, we can cover that next week, because that really fits into our analysis session. We'll actually get to run the analysis now that we've reviewed the data. So hopefully we'll be seeing you then. Bring any questions you might have then, or shoot us an email in the meantime. So thanks everyone, and have a good day.